So these laws of indices, which are on page 41 in the textbook, are here. It's worth having those to refer to. We use those a lot. And so it might be worth putting them on a piece of paper and putting it at the beginning of your notes for something to refer to. I think eventually, having used them enough, you'll know them, because they're not that actually difficult to remember. The main ones are the first two. All the other laws of indices are derived from those first two. So there are, we say, 6 laws of indices. Yeah, well, if you want a printout of this, all these notes are going to be printed and put on the site with the others, so you can always print this page out afterwards. Yeah, so you can do that. It will be on the website. But it's worth having these there. What I want to do is to just look at a few of them, see how they're arrived at, and then maybe leave you to show how some of the others are arrived at. So, let's make a start. So, these laws of indices refer to numbers, of course. A and M, all letters that are used now, always represent numbers. So, this is a number, this A that I've got here, and so is M. A is what's called the base. And M is the index, which is why it's called the laws of indices, or power. You're more perhaps used to seeing it written as a power. So, for example, 3 to the power 4. 3 is the base, 4 is the power or index. And hopefully you know what 3 to the power 4 means. What does it mean? Three times 3, you're right. 3 times by itself, 4 times. It does not mean 3 times 4, it means 3 times 3 times 3 times 3. So it's a shorthand way of writing that. If I write 4 to the power 3 multiplied by 4 to the power 2, if you think about what this actually means, it means 4 times 4 times 4, right, times 4 times 4. So in other words, I've got 4 to the power 6. So if the base is the same, and this is the key thing, so long as the base number is the 4, then what do I do when I'm multiplying numbers? I add the powers. 3 plus 2 is 5. What am I writing 6 for? Yeah, 5. Okay? Which is what the first law of indices is saying if we look at it. A to the m times a to the n equals a to the n plus n. That's all it's saying. It only works if a is the same, and that's implied here. We don't know what the number a is, but in this, it's the same in both. That's the important thing. And so we then add the powers. And in a similar way, if I divide, then I subtract the powers. So the second law of indices say a to the n divided by a to the n. And if you write it down, an example like I've just done here, 4 times 4, 4 cubed over 4 squared. Let's do, 4 cubed over 4 squared. That's going to equal 4 times 4 times 4 over 4 times 4. And if we look at it, you can see that 4's cancel. 4's goes into 4 once, 4's goes into 4 once. I can do that twice, and I'm left with just 1 4. So the answer is 4. And to get that, I actually subtract the powers. 3 take away 2 is 1. So in other words, 4 means 4 to the power 1, which is something that's worth remembering. If you see a number on its own, the power is 1. So the second law of indices is saying to me that if they are divided, I subtract the powers. Remember those two things. If the base is the same, When I multiply, I add the powers. When I divide, I subtract the powers. The third law of indices comes from this. Let's look at an example of that. So for an example of the third law, 4 cubed and then squared. If we think about what these powers means, what does square mean? It means 4 cubed times 4 cubed, because square means times by itself. And now using the first law of indices, base is the same, I add the power. What actually happens is I just multiply the 3 by the 2 to get the 6. So we multiply the powers if I've got a base raised to a power, and then that's raised to another power. So the third law of indices is saying a to the m raised to the n is a to the m times n. That's what this third law is saying here. This one, not quite so easy to see how that arrived at, and this is possibly the one that is most awkward. Well, this one and the next one, actually. And they turn out to be the most useful. This one and this one are worth asterisking. And when we come to calculus, those of you who've done some calculus will know that to be able to differentiate something, we need to know these two laws of indices and use them in particular. And so they're worth getting your head round, okay? Let's look at the 4 first. A to the m over n equals the nth root of a to the n. That's what it's saying. A to the m over n equals the nth root of a to the m. Let me explain that. So let's look at the example for number 4. Oh dear. Right, the square root of 9 is 3. Times by the square root of 9 is 9. 3 times 3 is 9, okay? So let's think about this for a minute. And there's a bit of a logical argument here, so you need to focus on it, please. Okay? The square root of 9 is a number, 3, which when you multiply it by itself gives 9. The square root of a number is the number which when you multiply itself gives 9. So if we think about this in terms of powers, 9 to the power a half multiplied by 9 to the power a half, using the first law of indices, what do I do with the powers? Add them together. A half plus a half is 1. So it gives us 9, or 9 to the 1. Multiply. Dot or no symbol at all means multiply. So let's look at this. What I'm saying is that 3 times 3 is 9. We know that. The square root of 9 is 3. So the square root of 9 times by itself gives 9. But this also gives 9. 9 to the power a half multiplied by 9 to the power a half gives 9. So the point is that 9 to the power a half is the same as the square root of 9. They are the same thing. And I could use a similar argument for the cube root. The cube root of a number is a number which when multiplied by itself twice, what's the cube root of 27? 3. Multiplied by the cube root of 27, multiplied the cube root of 27 is 27. But if we think of it in terms of the laws of indices, 27 times to the power of a third multiplied by 27 to the third multiplied by 27 to the third must equal 27 plus a third plus a third plus a third is 1. So 27 to the third is the same as the cube root, and I'd have to put a little 3 here to say the cube root. So they are the same. Now, I've sought in trying to explain how this thing's arrived at. The bottom line is that this law number 4 is saying here that I can rewrite a root, this is in root form, as a fraction power. And that's all you need to remember. For example. So therefore, the cube root of any number raised to a power, say 2, equals x to the 2 over 3, using that law of indices. Because it doesn't matter what this number is inside here, the cube root, as we proved here above, means a third. So it's whatever's inside, x squared, to the power of a third. So it's x to the 2/3. How would I write, looking at one more example, the 4th root of x cubed? Yep. X to the 3/4. Exactly right. And that's the law. So all this explanation comes down to remembering this law. And there's one little thing that I always say when I talk about this, and that is, if I've got this, the 4th root of x cubed, and I'm going to turn it into a fraction, well, which number goes underneath in the fraction? The root goes underneath, and that's the root in this case, the power 4. So that's a 4th root. And roots go under the ground, so that must go underneath in the fraction. So that's the way to remember, or one way of remembering which way round it goes. Is it 3 over 4 or 4 over 3? It's 3 over 4 because the roots go underneath. Then it would be x to the 4 over 3. Yeah, it's whatever the root is. So if this was the cube root of x to the 4, it would be x to the 4 over 3. What does the 5th root of x squared equal? Somebody on the back. X to the 2/5. Middle bench. Right, x to the 3 over 2, good. So in other words, if there is no number outside the root, that means the square root, so therefore the bottom number is a 2, okay? Middle at the front bench. No. What's the number that goes by the x? If there's no number there, it must be a 1. And if there's no number outside the root, that must be a 2. So x to the half. That's a common one, okay? The square root is x to the half. Okay. We'll pause there, and I will have a look at the last 2 laws of indices after the break.